Good evening, everyone. So today I'll be giving a small tutorial on transformers, and the intention is to just cover it in slight detail. And all the material that you see here is mainly just an amalgamation of all the blogs that you find over the net. There are some wonderful blogs, but this is just something that I felt I could share, and hopefully it kind of helps you understand the transformer in slightly more detail, right? So moving on to transformers, currently, like you would have definitely heard of applications like or models like GPT-4, Chat GPT making the news, and for a couple of years, I think transformer-based models have definitely given us extraordinary results. And at the core of all these models is the transformer architecture. Hence, understanding that in detail will help us go a long way in understanding these models too, right? So it has mainly applications in natural language processing, but also like with vision transformer, it has also made quite a lot of breakthrough in computer vision applications. So this is just a diagram of the evolution of the transformer architecture. Many of you may already know it, but I mean, this hasn't happened overnight. I mean, the ideas which you see in the transformer architecture have developed over the years. So if you look at the top left, you will have the simple RNN or the vanilla RNN, which kind of had its own disadvantages while training sequence models, which was slightly corrected by the LSTM. And later on, the gated units were, so GRU models were introduced. And then there was a phase even where these models, these recurrent models were used with attention, the attention mechanism, which is at the core of the transformer, which we'll see later. But even the sequence models were trained with attention. And only after that did the research or the famous paper that got published is where you could just use attention and basically train these sequence tasks very efficiently, because as you all know that for the recurrent neural networks, the problem of parallelization was very critical, right? I mean, we'll have to train it one sequence at a time. However, attention kind of opened up all the possibilities of parallelization, although it requires definitely more data. But with the computing power that is available these days, it's possible to train these fairly efficiently. Right. So this is just a very brief evolution of the transformer architecture. Just looking at the architecture diagram, which we see in the paper, we see this block fairly frequently in all the tutorials which have transformer. And this is the core or the core layout of the transformer architecture, right? So let's just take a minute and try to understand this in more detail. So let's look at the diagram on the left. What we see is we see one small block and one slightly larger block, right? So the transformer is mainly there to solve problems or sequence problems, right? So the block that you see on the left is basically known as the encoder block, and the block that you see on the right is known as the decoder block, right? And if you can see, there is this line which kind of curves over the encoder and gets passed on to the decoder. So in some way, information is passed from the encoder to the decoder. And then at the top, you can see output probabilities. So there are some probabilities that are thrown out by the decoder, which helps in solving these problems. At the bottom, you would see something called the input embedding that goes as input to the encoder, which is clubbed with something called positional encoding. And to the decoder, it's pretty much similar. So, but it's kind of named output embedding, and which is again kind of clubbed with something called a positional encoding, which we'll see later, right? So just to get to kind of in very generic terms, like what after kind of GPT-4 and Chat GPT have broken through, like we hear a lot of prompt engineering, right? I mean, this jargon is kind of all over Twitter or all over the net, right? So this prompt is nothing but what goes as input to the decoder section. So just to keep in mind a small like fact that what you see here as outputs, right, which is going as input to the decoder, is nothing but the prompts that you give in these various models when you try out these models, right? So, and on the right is just a very top level diagrammatic view of the two main parts of the transformer architecture. One is the encoder and one is the decoder. So breaking this down into parts that we need to dig deeper, um, the two main blocks, as we have seen, encoder, decoder, and then slightly important is the pre-processing as to how the inputs actually go into the transformer, and the output processing, post-processing is fairly kind of simpler. It's kind of all the normal layers that you have when you train a neural network. So we'll be looking in slight detail in this encoder decoder block and the pre-processing steps. First question is like, why are there these two blocks, right? Encoder and decoder. And to just get a very intuitive or very clear view is to understand what kind of tasks are we trying to solve in our normal daily problems, right? So if we take the field of natural language processing, and this screenshot is from the Huggingface library, which I'll just in some time navigate. So you see problems like text classification, question answering, summarization, text to text generation, right? And each of these problems merit a different kind of treatment. And you would soon see that it's not always the entire transformer that is used for each of these applications. So in many of the applications, only the encoder part is used. In some of the applications, only the decoder part is used. Whereas in few other applications, we need to use both the encoder, decoder, both those components and the entire transformer architecture, right? So if you have not heard of the, but I'm pretty sure like everyone's heard of these models, at least the GPT model. So it's just kind of good to know at the start that GPT is basically an only decoder model, right? Whereas BERT is an only encoder model. And there's a model called T5, which is used for text to text generation, which has the entire transformer architecture, which has the encoder and the decoder built into it, right? So even a model like GPT has only it's an only decoder model, right? And if you see just like a very diagrammatic view, it's the decoder part, the taller part on the right, which is throwing out probabilities, right? So in some sense, that is the generative part. The encoder is only encoding information, right, of one sequence, whereas the decoder is also taking a prompt here, as we have written output, is taking a prompt and then encoding, say, the prompt in general, like up to which the person has written the sentence, and then throwing out probabilities of the future words in the sentence that can occur. So you can kind of think about this decoder part as the generative part, which is used in models like GPT. So given that we just have around an hour, right, to cover this tutorial, the best way obviously to learn would be to implement the entire transformer architecture from scratch. And I think there's a wonderful blog doing it. But another way would be just to read the paper. And another way could be just to, actually dig deep into, say, a library like PyTorch, see how the model exactly looks like, and at least try and write a simple function to count the number of parameters. Because as you will see that this entire transformer architecture is nothing but a bunch of matrix multiplications. And if we understand each dimension at each layer clearly, I think it will serve us good in understanding the transformer slightly better. So what we'll do today is try and derive just a simple formula to calculate the number of parameters in any transformer architecture, right? Yeah. So this is the output that you will see from the PyTorch library if you call the built-in transformer module, right? So the one that you see on the right, on the left, is the detailed output of how the model is internally, and the one that you see on the right is basically the number of parameters in each of these layers. So we would have heard recently that we have some billion parameter model coming out, 175 billion parameter model. So let's dig deep into some of these models and see actually how many parameters they are, which layer takes up the most number of parameters, and why are they so, right? I mean, why are so many parameters actually required? So before that, I think I'll just try and navigate through the Hugging Face library. Uh, Hopefully my browser is visible. Yeah, so this is the Hugging Face library homepage, and Hugging Face is an open source library which has done an excellent job in kind of building a very easy interface or easy API for us to try out these transformer models, right? And to use it very conveniently. So they have the entire workflow coded in their API, and it's very easy to search for models now, data sets, and just download models and start using it for your application. So if you go to the home page, you will see on their search bar here where it's written search models, data sets, and users. You can basically search for any model, right? So let's click on the model tab and let's see what we get here. Yeah. So just enlarge this a bit. So their models are very well classified according to the applications. So you have a computer vision tab here, and inside computer vision, what exactly we want to do, we can basically click that tab and get all the models related to that application. So the screenshot that I showed you previously was regarding natural language processing, and you have these host of applications in NLP that you can solve through transformers, right? So if you go to text classification, the top you will see various BERT models, and as we saw, right, BERT is nothing but an encoder only model. Obviously you can combine the encoder and decoder and build something on your own for any text to text generation using the BERT architecture, but as itself, like, the models that you see here are basically encoder only model, right? So going back to the presentation, yeah, so let's what we want to get to is a small function which will basically help us calculate the number of parameters in the transformer module of, say, PyTorch, right, which is basically the source of truth. So for that, we'll break down this entire architecture into subparts. Like, there are some recurring subparts that you will see, right? So if you see the lower bottom, you will see that there is something called input embedding, output embedding, positional encoding. And these are all pre-processing steps that need to be done to be fed either to the encoder or the decoder. So we'll understand this too in one go, called as the embedding layer, and we'll try and derive a formula as to how many parameters or trainable parameters are there in the embedding layer. Similarly, if you go into the encoder block, which is the left block, right? So you have something called a multi-head attention, then an add and norm layer. So together, these two blocks, we'll call this the attention block. So attention is the core computation that happens inside the transformer architecture. And if you see the encoder block, it's good to note that there's just one attention uh, basically block here. Whereas in the decoder, you have something called the mass multi-head attention, and then you have another multi-head attention on top of it, right? And on top of both these attention layers, is basically a feed forward layer which processes the output from the previous blocks. And then at the end, you have your normal linear and softmax to output the or to throw out the output probabilities, right? So if we see, we have two attention layers. There is something called as masked attention. Let's see if it's anything different. And then we have two blocks of feed forward networks, right? Which one is for the encoder and one is for the decoder. And this NX that you see at the sides of the encoder and decoder, they are nothing but like in say CNNs or in RNNs where we could replicate that block multiple times. So similarly, we can choose to have basically n layers of these encoders or decoders, and we can keep replicating them to basically make the model more flexible, right? So, right. So let's start with the embedding layer. Okay. And what is basically an embedding? So just quickly, I mean, say we have a large corpus, right? And we somehow need to find out or trim down from or get from that corpus a limited size vocabulary, right? So larger the vocabulary, we will have too many words, will basically have too many vectors, and it can be very computationally intensive, right? So once we decide on the vocabulary, and I'll just in a moment tell you how usually it is done. But say now we have an input sequence, right? And let's keep this to NLP. So let's say we have some sentence that we want to classify. So the sentence that you see here is that transformer architecture follows an encoder decoder structure. Now this sentence somehow needs to go into this transformer in some numerical representation. And we all know that we can have a word level representation, which can be as simple as say one hot encode a word, right? But now if we think about it, if our vocabulary size is extremely huge, so usually these models have vocabulary size of up to 50,000, then you will have a matrix of 50,000 cross 50,000, right? Storing basically all those one hot encode vectors, which may not be like each word representation is basically a 50,000 dimensional vector, which may not be the most efficient way to encode it. So here is where embedding comes in. So embedding is nothing but a lower dimensional representation of the one hot encoded vector, right? Your entire corpus. And we can fix the size of the dimension. So more the size, more relation between the words we can basically capture, right? Now, in the transformer architecture, as you had seen, there is something called as positional encoding, and there's something called as input embedding. So what we have traditionally known is that we say have a word, um, and if we want to find the embedding, we basically insert an embedding layer and make it a trainable layer. Like there is no point in us giving some predefined numbers to it, but we basically just make it as a parameter of the model. And then depending on the supervised task that needs to be performed, with the help of back propagation, we'll get the appropriate word vectors, right? But this is only the token part of it. Now, if we see the architecture closely, you will notice that what we send in as input has no notion of a sequence, right? We are sending the entire sentence as it is into the transformer. So even if we jumble the words in the sentence, it is basically not going to make any difference, right? So, but this is very different in the RNN scenario where we input one word or one token at a time. So the concept of sequence is naturally fed into the architecture, right? So if say something comes first, it will be fed into the architecture initially as compared to the other words. But here we are giving the entire sentence. So if you gave transformer architecture follows an encoder decoder structure, it would be same as architecture encoder decoder structure follows and transformer, which doesn't make any sense, but it would have the same representation if we only stuck with token embedding. But the paper, if we see the paper, they introduce something called as position embedding, and it is slightly involved, the math in it. I mean, it in itself is a slightly hard to get some intuition as to why they have come up with these particular formulas. But the claim of the paper is that if you add them, if you add the token embedding and the position embedding, the essence of the token embedding is not lost, but it also encodes for that particular word which position it is in, right? So in this way, we are able to understand that whether transformer is the first word in the sentence or the 10th word in the sentence. Now, the good thing about this is they have given us a suggestion of how to use. We can also keep the positioning, we can just initialize the position embedding randomly and make it a learnable parameter. And that is what is done in many of the architectures. Like, for example, GPT-2, the position embedding is something which is learned and it doesn't basically use these formulas, right? So that is, I think, much easier and more intuitive to understand. It's exactly similar as the token embedding, but it's only for the positions, right? So let's see how these matrices actually look like. So token embedding is for all the words in our vocabulary. We would have basically a vector. Now, instead of a big 50,001 hot encoded vector, we believe that, say, a 768 or even lesser 5112 dimension vector would be enough to represent that word, right? So your entire embedding matrix or learnable parameters would be vocabulary into the size of the embedded vector, right? So that is V cross D, if V is the size of the vocabulary. Now for position embedding, it will be it depends on the maximum sequence length that the transformer or the architecture can basically accommodate, right? So if, say, the maximum allowable length of the sequence is 20, then you would have 20 position embedding vectors, one for position 1, 2, 3, and so on till 20, right? So these two become basically learnable parameters. So one would be a V cross D vector and the other would be an N cross D vector, right? So let's now look into some code and see, just dig deeper and see how these parameters, or how actually are these parameters there in the Hugging Face models or not, right? So let me just open my, so this code will also be available on the net, but I've just kind of collated them and put them in one notebook. So here we are just initializing the Torch. We're importing the neural net library from Torch, and there are these two helper functions which we basically get from this issue on Stack Overflow. And it's a neat way of basically computing the number of trainable parameters in any PyTorch model, right? So the first function, it will basically iterate through model.parameters, and only if the parameter requires a gradient, that is, if it is a trainable parameter, then it will basically sum up the number of elements in that tensor. And count parameters tab, which output I'll just show you, is it gives you a layer wise bifurcation of how many parameters are there in each layer. So going back to the notebook, let's initialize. So this is nn.transformer is basically the built-in PyTorch transformer module. If we want to build any transformer model from scratch, we basically just need to initialize nn.transformer and then feed in our training data set. Now here there is something called nhead equal to 16 and encoder layers equal to 12. For now, let's keep this 16 aside, but I'll show you one thing. And the number of layers is exactly what we had discussed earlier, is this n cross, right? So this is number of encoders layer is 12. By default, it keeps the number of decoder layer as 6. So let's see. Now here, for the transfer, to make a forward pass, we need the source and the target. Now, what is the source and target? This is nothing but our input and output, right? Because this is the entire transformer architecture that we are initializing, right? And for the encoder also, we need an input, and for the decoder too, which I told is nothing but what we hear in today's jargon, like prompts. That is basically the input to the decoder. So this is just a dummy transformer. There's not much meaning to it. But let's just initialize some random vectors and see what happens, right? So after we have made, so this is the forward pass, right? Here is we are doing one forward pass of the architecture, right? And if we see the output shape, it's exactly same as the input shape, right? So if the max output sequence length is 20, right? And 512 would be your embedding size. Now, if we call the function count parameters of this transformer model, let's look at. So it has around 63 million parameters. And what we'll try and do is basically break this transformer model into parts and come up with a function that gives us exactly the same number, right? So we have 63 million parameters in this model that we've just initialized. And if we look at each of the layer, right? So this function, that helper function that I showed you, it basically shows in each of the layer how many trainable parameters are there. So what I've done is, because you'll just get a truncated output here, I've just put this into a text file, and now we can basically see each of the layers, right? So this itself gives us a good view of actually how the transformer is implemented, just from the naming conventions, right? So if you see encoder layers dot zero dot self attention, then there is a linear layer, there is a normalization layer, so on and so forth. But first thing to note is that the same block, right? If you just take this block, this is getting repeated just once, there's another, second, third, fourth, fifth, sixth, and you will find that there are basically 12 layers, because we gave the parameter as 12. Now for decoder layers, we didn't give anything. So by default, it gave 6 decoder layers. But in the same way, it has one block, and basically it just keeps repeating that block again and again, right? And we have 6 decoder layers, and the total trainable parameter comes to be 63 million, right? But here we don't see any mention of the embedding matrix or nothing of that sort, right? That is because in the transformer architecture is just the encoder decoder layer. The way you put it in, right, is just the outside part of it. It is not inherent into the transformer architecture to have this encoding, right? Hence, when you initialize the transformer layer, you won't see the embedding layer initialized, right? So let's go back to our code and let's see how we can match our embedding learnings. So what we've learned so far is, for the embedding layer, we would have one token embedding, which is vocabulary size into the embedding dimension. And the another is the position embedding, which is number of positions or the max sequence length that is allowed into embedding for each of those positions. So what we'll do is, let us initialize a GPT-2 model. Now, if we initialize a GPT-2 model from Huggingface or any other model, it would have a way to create this vocabulary. Because how do we actually go about creating the vocabulary, the word representation? Where should the threshold be to cut off if you're doing it based on frequency, right? So that itself is basically an algorithm that is inherent to the particular model. So in GPT-2, basically it will be done in a certain way. Maybe in BERT, it will be done in some other way. So there are various ways to create this vocabulary or the word representation, right? So if you see, whenever in Hugging Face you kind of load a model, you'll have to do two things. One is initialize something called a tokenizer, and the other is just load the weights of the model. So let's go ahead and do both, right? And how do we get, like, how do we understand that this is the way to call a GPT-2 model? So this is something that you can go to the Hugging Face uh, website that I showed. And if you type in, if you want to search a model, you can just type in the name. And if you search for GPT-2, then you basically get GPT-2, and they have a very, very well structured model card, right? So let's keep this tab alive for some time, and they will give you clear instructions on how to basically use this model, right? So if you see here, they load the GPT-2 model the same way that how we have done. They give an example text and they encode the text using the tokenizer, and then it is put into the transformer model. So that step of whatever token embedding plus positioning embedding is done by the tokenizer, right? So now now the model has got initialized. If we count the parameters, right, and if we see layer by layer what parameters are there for the GPT-2 model, here, because we'll see WTE dot weight and WPE dot weight, right? And then basically H dot zero, the same way how we saw the transformer architecture, the same repeatability starts occurring. But these first two, right, are nothing but your token embeddings and position embeddings. So TE is nothing but token embeddings and PE is nothing but position embeddings. Now, if you see, the total number of parameters in GPT-2 is 124 million, right? And if you go to the model card, search for 124, they will also give you that, this is basically the smallest at 124 million. So it's kind of matching. We've loaded the correct model. But it's important to know that of the 124 million, right, 338 million is basically nothing but your token embeddings. So the embedding step does take a bulk of your trainable parameters, right? And position embeddings are comparatively lesser because it just depends on your max sequence length. Now, how have these two numbers come around? You see this like 38,597,376. How has this number come around? Now, what we saw in our slide is that the embedding is nothing but vocabulary size into how much, what is the dimension of the embedded vector. Now, from where will we get this data, right? So we can check in this model card itself, like what is the vocab size. So if we see here, right, in pre-processing, in the pre-processing tab, so here it says that the texts are tokenized using a byte level version of byte per encoding. This is an algorithm and a vocabulary size of 50,257, right? Now 50,257 is the size of the vocab, and the inputs are sequences of 1,024 consecutive tokens. So this is the maximum sequence length that is allowed for the GPT-2 model. Now, if we know the maximum sequence length, we should be ideally getting at least the position embeddings, right? Wait, but so we have 1024, right? Now, how do we come to know what is the embedding size? Like, what is the embedding dimension? If we just look at the next layer, which will basically be the input to the transformer, we see this number 768, right? So this is basically the size of the embedded vector for each of the position vector and the token position embedding and the token embedding. So if I just do 1024 into 768, right, we get this number 786432. it's exactly matching, right? And if I take the vocabulary size 7,257 into 768, that also matches the 38 million number exactly, right? So here we understood that how to basically calculate the number of trainable parameters in the embedding layer. Now, it is important that both the token embedding and the position embedding size, right, they need to be same because they are basically added. If you see the sign here, they are added and put into the transformer. So now let's move ahead to the next block. It is the main attention block, right? So the attention block is basically the core calculation of the transformer architecture. And to get an intuition, we can think of something like a recommender system where we have collaborative filtering and content-based filtering, right? So what is the difference between these two? So in content-based filtering, we know what the user likes. So already features for the users are created. And similarly, we know what kind of movie it is. So the features for the movies are also created. And we just try and match these two vectors and fetch similar or movies most likely the user will like. Whereas in collaborative filtering, creation of this feature is very tedious, right? We may not have always know what the user actually, the user also may not know, right? So as the user develops habits, the assumption is that similar users will watch similar movies. So just based on the watching habits of all the users, we are able to recommend what a particular user may like, because a similar user who has watched the same movies may have watched another movie which I may have missed, right? So the core of attention is to basically create something like a collaborative filtering, because the first step, we have taken words and we have embedded them, right? We have reduced the dimension space. Now to create features, we need an automatic way to create features, and that's what neural net basically does. We are not going to create, say, n-grams or trigrams or bigrams, right? We want the network itself to do. And that is what is at the core of this attention layer. So before we dive into the core of the attention, just if you see this diagram on the left, just to get things clear, we are inputting a n cross d matrix because n is the number of elements in the sentence, right? So like in case of GPT-2, we saw that number is 1024. Even if the sentence is not that long, the practice is to basically pad the sequence with dummy tokens, right? And what we get as output after the attention will also be n cross d. So what basically does this attention do if we are getting the same dimension vector? Now, let's say we have already trained the transformer, right? The embedding that we get for a word, it will be one vector. Okay. Now that one vector can only give you an aggregate meaning of a particular word. So say we take a word like bank, right? It may mean different in case of a river bank, as say if someone wants to basically draw some money from the bank, right? Now, if I have just one word embedding for bank, how is it possible to capture these different contextual meanings, right? And that is what exactly attention does. So there would be an aggregate embedding that we have learned, but given a sentence, if you pass it through the attention layer, if you pass the bank with river, you will get a different embedding for bank. If you pass bank with say money, you will get a different embedding for bank at the other end of the attention. And that is what basically our attention does, is take your aggregate embeddings and basically transform them into contextualized embeddings depending on the sentence that you feed, right? So it's keep this broad concept in mind. So let's just have a look at attention. It's slightly hard and it's better drawn, so I've just noted it down on paper. So let's say your vocabulary size is 4, right? So if your vocabulary size is 4, we have 4 embedding vectors, right? After it has passed through token plus position embedding, we've already seen that. And let's say the dimension of the embedding is D. Now, from simple matrix multiplication, we know that dot product is a good way to capture the similarity between two vectors. What the attention layer is doing, it's saying that, okay, I have a word. I want one way to do it is to take dot product of that embedding with the other words, right? So you see here, right? V1 dot V1, V1 dot V2, V1 dot V3, V1 dot V4. What we will get, so dot product of two vectors will be just one score, right? So we'll get 4 scores. Now, these scores need not be normalized. So we pass them through a softmax layer, or just for now, just assume that we are just normalizing them. And we will get these weights so that they add up to 1. It will be a probability distribution, right? After passing through the softmax layer. So once we get these weights, we can weigh each of the embedding, right, of each word with these weights. So say W11 will be multiplied by V1, 12 by V2, so on and so forth. And we get a contextualized word vector for each word in the vocabulary. And this is with respect to one of the words, right? We can do this for each and every word. And at the end, we can aggregate all these contextualized embeddings to get like kind of a marginal sum and get the contextualized word vector for, say, the word bank, right? But so these are all the basic operations that are done in the attention layer, right? So again, drawing parallels to collaborative filtering like a user and movie, we want to see which word occurs more frequently with which other word, or which word has a very similar occurrence as some other word. So nouns may have very similar surrounding words or some faraway context too, because we have 1024 tokens, right? So we have a large span that we can capture. So these are the basic, but the problem is that if I'm taking the dot product of the embedding with itself and coming up with these scores and then weighing it, there is no learning, right? This is just one way of getting a contextualized word vector. But this may not be the best way to get it, because why should I just sum the contextualized word vectors? Why should I just take a dot product and not weigh V1 or V2 according to some supervised metric that I have, right? So there are no parameters to learn here. So this is kind of not very useful, right? So now let's say I want to introduce some parameters like how we do in a normal linear regression, right? If I ask you, like, guess the age of, say, a person, and you have many features like, say, the height, right? The weight, you just won't sum up, right? You will take data, give potentially give some weight to age, to height and weight, and then try to derive those weights from the data. So this is exactly what we'll do. Instead of just providing the embedding vectors, give them the weights, right? Give them the weights and then see like how it trains based on the supervised learning that we will do, right? So for each of the operations that we saw here, in the first case, the dot product, that a word is being compared with another word, let's introduce a weight called mk for the word and mq for the word that it's getting compared to. And just to note here, it is getting compared with itself too, right? So everything remains the same, just that we have added these weight matrices in between the operations, right? So in total, if you see, right, how many weight matrices we have added. So in the dot product, we'll need to add one for the word input and one for the word being compared. So these are shared across all the words for a particular layer. Across the layers and across heads, which we'll come to, they are not basically shared. But so we have two matrices here, And then instead of taking the sum, right, there is no real good way to show that we should take only the sum. So introduce another word, another weight vector called MV, right? And basically learn these three matrices as learnable parameters, right? So if you see here how basically the embedding is going through, I can show a better picture. Yeah. So if I just maybe zoom in, so this is our input, right? N cross D, which is our embedding size. Now we have basically, we want to multiply each word with each other word, right? So from each word, we will be multiplying with the WQ, which is MQ there, MK and MV. So we'll get three matrices called QKV. Now this is a jargon that is used in the paper and for attention. So Q, K, and V stand for query, key, and value. And this is like basically fetching something from a database, and that's how it's come, but we can just ignore it for now. So these three matrices, query, key, value matrices, if you see their dimensions, so one would be N cross, so number of tokens would always remain. After getting these weight matrices, we will have N cross DQ, N cross DQ, and N cross DV, right? Now, why is the weight matrix matrix here of the same dimension for the key and the query? Because if you see in the previous slide, yeah, so if you see in the previous slide, this is a dot product, right? And we are introducing this weight matrix. The dimensions need to match, otherwise they won't satisfy matrix multiplication. And hence you see that for the key and the query, you have the same dimension. And in general, they keep, I mean, all the architectures to simplify things also keep the dimension of the value the same, but it is not required per se to have the same dimension for the value. If we zoom into the left bottom picture, right, so this gives a good overall view of what is happening. So we have one word, I can say one embedding, and it gets basically, from that embedding we generate three matrices, right? We have three learnable matrices, WQ, WK, and V. Take the dot product of Q and K, query and K, which has vectors for all the words, and then that scaled dot product will basically tell us how similar one word is to the other, normalize it with a softmax, and multiply the embeddings again, right? And what we get is a contextualized vector. So this is basically the attention mechanism. So this has been developed over the years, and hence maybe once we see it first, the question is like, why is it so complicated? But main thing to note is that the at the essence of it, it is something very it basically fastens the. So takeaways are that the attention layer takes in input and aggregate embedding, and it is giving you a contextualized word vector. So in many cases, you will see that they analyze this contextualized word vector, and we have some interesting findings usually, right? The layers here, right, or the architecture that we pulled out, you will have something called the multi-head attention. Now, it is seen that one attention head is maybe not enough to calculate all kinds of context within a sentence. So if say bank is the bank may be related to money and river, and but someone says banks on you or something of another context or another words or some other words which it has context with may not get captured in the same attention head. To provide more flexibility, we have basically multiple heads that you can instantiate, right? And the numbers are, I think, like as we saw it, we can have any number of heads. The only thing is that it should be a multiple of the dimension of the embedding dimension, and we'll just see why it is just a convenience that is required. If you see the diagram on the right, right, you'll see that the same attention or the dot product that we did, there are H layers of it. And all these are trained parallelly. There is no dependency on each of the layer. What we get as output from each head is basically concatenated and then passed through a linear layer, right? What they try and do is that the contextualized word vector has a dimension of dv. Now dv is the dimension of one word vector coming from one head. If there are 10 heads, the concatenated vector would be 10 dv, right? If there are 20, it would be 20 dv. But the input dimension or the embedding after token and positional embeddings, the size was d, right? In case of GPT-2, we saw that it was 768. What they make sure is that the dimension of the contextualized vector into the number of heads should be equal to 768. So that when they concatenate all the contextualized word vectors from all the heads and get one big contextualized word vector, that should also be of the dimension 768. So that just eases the computation. So say you have 768, right? And you instantiate 12 heads. Then you will have a contextual word dimension of 64, right? So number of heads has to be a multiple of the number of the embedding dimension. That's the only reason to keep this multiplication kind of uh, in sync with all the parameters, right? So now coming to the parameter calculation, if we see, right, we have introduced 3 matrices, and these matrices are of size d cross dk, right? And where say d is the number of the size of the embedding dimension. So where 768 dk, as we saw that dk and dv of the value is also the same, right? Say 64. So this would be of size 768 cross 64. To get back the same size, even query would be of the same size, just that it would be 64 cross 768. And we would also have value of the same size, which is 768 cross 64, right? So if we see, we have basically 3 matrices, query, key, and value, all of sizes d into dqqv, which is basically 64. D is equal to 768 and dqqv is 64. Because this is a matrix multiple or a neural net, right? We shouldn't forget about the biases. We just don't multiply. We also include the biases, right? So we have 3 matrices, and each matrix multiplication will be d cross dqqv plus dqqv, right? So this term that you see here is nothing but 768 into 64 plus 64 for the biases, right? And these 3 matrices is for one head. So depending on number of heads, it will get multiplied by those many heads, right? And after doing all this, we have the concat and linear layer. So after concatenating, we know that the vector size would be same as the embedding dimension, which is 768. So the linear layer would be 768 cross 768 plus the bias, right? So if we multiply, if we open these brackets, we will get 64 into 12, which will again be the dimension of the input embedding. So we'll get 4 into d square plus d, right? So what we've done is basically come up with a formula for the number of learnable parameters in the attention layer, right? So it is just, if you see, it is just dependent on the input dimension of the embedding, right? Because it is 4d square plus d. Now, just to get a sense of how these architectures vary, right? What we saw was GPT-2, right? So it had 12, it has basically 12 decoder layers. We know that GPT-2 is a generative model. is a decoder only model. And if you see model dimensionality, which is 768, which is the size of the embedding, it's basically 768 for GPT-2, and it keeps on increasing for the larger and larger models, right? Now, what all have we covered so far is in the attention is we've covered the embedding part, we've covered the attention part. Now the only block, that main block that is left, is this small feed forward block. A feed forward block is just to give more non-linearity to the entire architecture and to come up with, like, just to have more flexibility in the entire architecture, right? So if you see the feed forward block, it's like a very normal block where the input from the attention layer is basically coming. So the input from the attention is an n cross d, right? What we saw here. We basically send in embeddings, we get back contextualized word embeddings. And that goes in as input to the feed forward network. What it does is basically just widens the number of dimensions slightly and then again brings it back. So like a normal feed forward network, and that size can basically be decided. But whatever be the size, basically there is kind of an increase in dimensions and again coming back. So there are two weight matrices, right? So it would be D, which is the again the dimension 768, into whatever we decide as the bottleneck layer size, plus D is for again the bias of the second matrix, and D cross DFN again would be the weight matrix for the first one, but it would be with DFN biases, right? So what we have at the end is 2 into D into DFFN plus these bias terms. If you see, like, the bias terms actually can be neglected because here we are dealing with dimensions of 768, right? So if we multiply 768 cross 1000, that number is significantly higher than the bias term. So for all practical purposes, we can just get rid and come up with an approximate formula, right? And the last layer is this normalization layer, which is specific to transformer architecture. It is called layer normalization. So there are other architectures where batch normalization is done, but here basically layer normalization is done, which is nothing but because there are so many moving pieces in the transformer architecture, we may not always get well distributed outputs at each and every layer. So very similar to batch normalization, it basically again centers the distribution of the output. So it subtracts the mean, divides the standard deviation, and there will be basically two parameters to do that, right? And the two parameters would be of dimension D, because it has to do for every dimension, it will need to maintain it. So beta and gamma, say, are the parameters, then those two vectors would also be learnable, trainable, and they would incur an additional parameter, which is basically twice 2 into D. So we are actually done with our formulation of all the trainable parameters or all the moving parts. So just to revise once more, if we go back, we have the embeddings, right? So embeddings, as we said, it would be vocabulary size into the fixed dimension for whatever is fixed for that architecture. Plus for position embeddings, each position would have an embedding. For the attention layer, there are these three matrices which are created basically to create the features and to get similarity between the words. So that comes out to be 4 into D square plus D, as we saw it. And then the feed forward network, which has another bottleneck layer. So we have another two weight matrices, which is approximately 2 into dimension, which is 768 into the bottleneck layer, right? And the last layer that is remaining, which is very specific that we see in the decoder, is the mass multi-head attention. Now, it's just important to understand what this masked multi-head attention is. It is exactly the same attention layer for the decoder input, because it's the first thing that hits the decoder input. But why is it masked? Because when we give a prompt, right, or like whenever you're giving a prompt to chat GPT, it only has the view of the sentence till you have typed, right? It doesn't have visibility into the future. But that's not the way the training is usually done, because for efficiency, the entire sentence is basically fed into the architecture. And in order to mask some of the sentence, we have this mask multi-head attention. Okay. So it's just making the architecture blind to words that will come in the future, because that is not something that the decoder is going to actually see. So if we see the masked multi-head attention, so it's basically this kind of mask that you'll put, right, diagonal. But what is the value that you will put? Basically, we put minus infinity for the values that we want to mask, right? And it just we make a small correction in the attention formula, where we add this mask matrix. So wherever we want the parameters, we keep it as 0, and other places minus infinity. Now, why minus infinity? So if you see the diagram to the left, where we have queries, keys, values, then come up with the score, and then we have a softmax layer, right? So that softmax layer will basically zero out the minus infinity, and it will have no impact on the final embedding or the score, right? So that is just one small detail. So number of trainable parameters don't change. It will be exactly the same for the attention layer. And just that this extra mask is applied while training, right? And this is another small detail, is something called cross attention, just to make sure that we complete the entire architecture. So what we've seen till now is the attention layer inside this block, right? But encoder block, or say the mask multi-head attention, would also work the same way, but just with the masking matrix. But for the connection between the encoder and decoder, there is this multi-head attention, which is basically taking the input from the encoder and also the decoder, right? So here, where we have the query, key, and value matrices, the query matrix basically comes from the encoder, whereas the key and value matrices, they come from the decoder, right? But because the dimensions are maintained usually across encoder and decoder, so there is no real change in the formulas that we have derived. But it's important to know that the query vector, or the query, comes basically from the encoder, and the encoder sends it to all that word, or that output will be sent to each of the attention layers in the decoder, right? So that is just one. And final predictions, as depending on the task that we want, we basically add another fully connected layer and basically output the probabilities, get a distribution across the world. And also another detail is the skip connections. Like, it's hard to cover the entire architecture, but it, just so that we see kind of the skip connections here, right? So skip connections are nothing but where the input is also again given back to the output, so that there is a smooth gradient that is created while training. Um, so these are nothing but residual connections. And you can see that with skip connections, your loss function basically has a much smoother area than what it is without skip connection. Because remember that attention is basically like a filter, right? I mean, it will just filter out the part that is needed. So sometimes the changes are quite jittery, and that may result in very spiky gradients. So if we have the input again fed back to the output, then it results in slightly smoother training. And other than the training course, even like just so that the network remembers the input sequence more appropriately or more in a much better fashion, the residual connections help, right? So before like we end, we'll just look at the final calculation of what we came with and see if it matches the number, right? So we had initialized our transformer architecture and it had 63 million parameters, right? Now, even you can see that if I change the number of heads to 8, right, the parameters won't change. They will remain as 63 million. And that is because of that calculation which I mentioned, is that number of heads into the dimension of the query key and value will always be equal to the dimension of the input embedding. So internally, they are maintaining the dimension. So irrespective of how we change the number of heads, we can have less expressibility in a head and have more heads, or we can go with larger vectors inside one head and have lesser heads. So that's a trade-off. But otherwise, the number of parameters won't change. So let's see if we get this 63 million uh, number, right? So just so this is a small function. It's basically from one blog, and he's kind of neatly done it, where he also gives us an approximate number, right? As I said, as I mentioned, that if we are doing a square of the dimension, basically the bias terms are not really, don't really matter. So if you see, we came up with a formula for the attention block, which was 4 into d square plus d. We came up with a formula or the number of trainable parameters for the feed forward block, which was 2 into d into the bottleneck dimension size, and the normalization layer, which is just 2 into d, which is our gamma and beta, right? And here, if you see it, like for an encoder, we will basically have one attention, one feed forward, and two layer normalizations, right? So if we go back here, right at the beginning, yeah. So we have one feed forward, one attention, and two layer. Here we have two attentions, three layer normalization, and one feed forward. So if it is a decoder, then we have two attention, one feed forward, and three layer normalization. Whereas for encoder, it has one attention, one feed forward, one normalization. So now we saw that this basically had 12 layers, right? If we look at the architecture, so it had 12 encoder layers and 6 decoder layers, right? So, and this formula is for the number of parameters in one layer. So let's just go back and let's write here count parameters for an encoder layer, right? And sec, yeah. So what we've done here, in addition, we've also instantiated a PyTorch only encoder layer with 16 heads. As I said, the head doesn't matter. And this is only decoder layer, one decoder layer with 16 heads. Now, if I run the count parameters, right? So the transformer count parameter D is equal to 512 and this is equal to 2048. These were the dimensions that we used, and we want the encoder, and there are basically 12 encoder blocks. To this, we will basically, sorry, to this we will add the decoder blocks, but there are only 6 of them, and we get basically the same number, right? So this function of ours, transformer count parameters, is basically calculating all the parts of the transformer architecture, and we are getting exactly the same number of trainable parameters as the PyTorch model. Also, we saw that we were able to match the embedding trainable parameters of GPT-2, right? From our understanding of the transformer architecture. So that is it. Like this kind of completes like a small dive into the transformer architecture just to understand the moving pieces. And the main rationale, I think, behind this architecture is still the basics of what makes the computation faster and what makes the training simpler, right? I mean, all these are efforts to have everything modeled as matrix multiplications, make each kind of function differentiable, and even the residual connections are to basically make the gradient smooth, right? So these are basically the three backbones or the rationale behind the architecture. There are some references which like have been compiled for this slide, and that's it. Thank you. And like if there are any questions. So I think one is, what is the data path? And I mean, is there any loop between them? How we extract features and output? Uh, so I like I just think we saw, right. So just that the data for the encoder has to be embedded using the position embedding. The position embedding is very important because otherwise the transformer has no clue as to where the word is. So that's slightly a complicated part, but the fact that it can be made trainable, which many of the big architectures have done. So, but that's the only pre-processing that you require. And basically everything is kind of made into a learnable parameter. Hence, the data required for transformers are huge, right? Um, then how much do you use this library in day-to-day work? I think for all text related applications, this is like Hugging Face we do use on quite a regular basis, because any pre-trained model, right, fine-tuning on any of these pre-trained model is pretty simple. So can import, I think they should be available on Collab. Yes. Is there any difference between attention and multi-head attention? No, so attention is uh, just the core formula that we saw, the QK transpose into V part. And many basically attention heads are given to one layer. And the only thing is that these heads are not connected. So they are basically allowed to be trained independently. And that's, I think, one of the beauties, because they will capture different kinds of context for the same word. um, and that is one main reason is what I've read is that because we apply the softmax layer right at the end, so softmax tends to divide or give more importance to the ones which are higher and completely subdue the ones with low probability. So there would be many words which would have maybe some significant context to the input word, but may not be able to come up due to the softmax layer, right? So hence the multi-head is kind of required. What is the difference between batch and layer normalization? So yeah, batch normalization, I mean, as the name says, it happens across the instance at a batch level. This is more at just the output level, like one of the layers, right? Where we have, so the if you see the dimension of gamma and um, beta, they are basically just the dimension of the input vector, which is D, right? So yeah, this is slight difference, but both kind of serve the main purpose. And I think batch normalization didn't work very well for the transformers as much as layer normalization did. Um, which are the LLM hyperparameters? That is like if you see the GPT-2 model increase, right? I mean, your basic parameters are the size of the embedding that you want. There is obviously vocab size, how much of the vocab you want to keep. Next, you have number of heads, so that trade-off between heads and what should be the internal basically size of the query key. And last is the number of layers, like how many layers do you want to kind of pile up. So GPT-2, I think, starts with 12, which goes on till 36. How to essentially build a custom language and train it for translation to basic bite-sized chunks of building blocks into major languages. So I think you will require the pair of actual, I mean, whichever language say you want to target, and your native language. So you'll need to have those sentence pairs. And if you kind of slightly explore the Hugging Face API, you will find it's pretty convenient to tune or build a model from scratch too, because all the architecture, the coding is already done, right? So you'll need to have those sentence pairs to basically train your custom translation model. Thanks a lot.